Welcome, curious minds, to Mechiversee. Today, we embark on a journey into the captivating realm of heat transfer, a fundamental process that shapes our world. At its essence, heat transfer is the movement of thermal energy from hot objects to cooler ones. It's the invisible dance of particles, the essence of warmth spreading through our surroundings. Ever wondered why your hand feels the heat when you touch a hot iron, or why your coffee cools down after a while? That's heat transfer in action. Join me as we explore three remarkable ways this phenomenon manifests: conduction, convection, and radiation. Conduction. Consider the familiar act of ironing. As you press a hot iron against wrinkled fabric, heat is conducted from the iron to the clothes. Conduction, the transfer of heat through direct contact, is at play here. The metal of the iron passes its thermal energy to the fabric particles, smoothing out the wrinkles in the process. Conduction involves the transmission of energy from higher energy particles to neighboring lower energy particles through particle interactions. It occurs in solids, liquids, and gases. In gases and liquids, conduction results from collisions and diffusion of molecules during their random movement. In solids, it arises from the combination of molecular vibrations within a lattice and the transfer of energy through free electrons. Consider the continuous flow of heat through the thickness delta X and area A of the metal table. The temperature difference across the table is denoted as delta T equals T2 T1. Experimental findings indicate that doubling the temperature difference delta T, or the area A, results in a twofold increase in the heat transfer rate through the table. Conversely, doubling the wall thickness L leads to a halving of the heat transfer rate. From these observations, we infer that the heat conduction rate through a flat layer is directly proportional to the temperature difference and the area, but inversely proportional to the thickness of the layer. The parameter K represents the thermal conductivity of the material, reflecting its capacity to conduct heat. Thermal conductivity, represented by the symbol K, quantifies a substance's capacity to transmit heat. To illustrate, iron has a heat conduction rate over 100 times greater than that of water. Consequently, we describe water as a less effective heat conductor compared to iron, even though water excels as a medium for retaining thermal energy. Another illustration of conduction involves a chilled canned drink placed in a heated room. Over time, the drink gradually reaches the room temperature due to the transfer of heat from the surroundings to the beverage through the aluminum can via conduction. The efficiency of heat conduction in a substance is influenced by factors such as the medium's geometry, thickness, material composition, and the temperature differential across the medium. Imagine sipping on a steaming cup of coffee. As the coffee cools down, you feel warmth rising. This is convection at work. Hot liquids, like the coffee in your cup, create currents as the warmer particles rise and the cooler ones sink. It's the reason your coffee gradually reaches a more palatable temperature, thanks to the natural flow of heat through convection currents. Convection serves as the mechanism for transferring energy between a solid surface and the nearby moving liquid or gas. It encompasses the combined impacts of conduction and the movement of the fluid. The swifter the fluid motion, the more significant the heat transfer through convection. When there is no substantial movement, the heat transfer between a solid surface and the adjacent fluid occurs solely through pure conduction. The presence of fluid motion enhances heat transfer but complicates the determination of transfer rates. Consider the scenario of cooling a hot block by directing cool air over its top surface. Initially, heat is conducted to the air layer close to the block, and subsequently, convection carries this heat away through the combined effects of conduction within the air, resulting from random air molecule motion, and the bulk motion of the air. This bulk motion replaces heated air near the surface with cooler air. Despite the intricacies of convection, the rate of convection heat transfer is observed to be directly proportional to the temperature difference. Newton's law of cooling conveniently expresses this relationship. where h represents the convection heat transfer coefficient. A_s is the surface area facilitating convection heat transfer, T_s is the surface temperature, and T infinity is the temperature of the fluid sufficiently distant from the surface. It is important to note that at the surface, the fluid temperature equals the solid's surface temperature. The convection heat transfer coefficient, H, is not an inherent property of the fluid but an experimentally determined parameter dependent on various factors such as surface geometry, fluid motion nature, fluid properties, and bulk fluid velocity. Forced convection occurs when external means like fans, pumps, or wind induce fluid flow over the surface. In contrast, natural or free convection happens when fluid motion results from buoyancy forces induced by density differences due to temperature variation. For instance, without a fan, heat transfer from the surface of a hot block involves natural convection, driven by the rise of warmer, lighter air near the surface and the descent of cooler, heavier air to fill the void. If the temperature difference between the air and the block is insufficient to overcome air resistance, heat transfer occurs through conduction without initiating natural convection currents. Radiation, the third mode of heat transfer, is exemplified by the warmth of the sun's rays on our skin. Unlike conduction and convection, radiation operates without the need for a medium. The sun emits electromagnetic waves that traverse the vacuum of space to reach us on Earth. Similarly, near a fire, the heat experienced is radiant energy, not requiring direct contact. Remarkably, radiation transfers heat at the speed of light and remains undiminished in a vacuum. This mechanism is crucial for the sun's energy to reach our planet. In thermal studies, our focus lies on thermal radiation, emitted by bodies due to their temperature, distinct from other forms of electromagnetic radiation like X-rays, gamma rays, microwaves, radio waves, and television waves, which are unrelated to temperature. At temperatures above absolute zero, all objects emit heat radiation. This emission occurs throughout the volume of the object, and whether solid, liquid, or gas, they all emit, absorb, or allow radiation to pass to some extent. However, for opaque solids like metals, wood, and rocks, radiation is predominantly a surface phenomenon. This is because the radiation from inside these materials can't escape to the surface, and incoming radiation is usually absorbed very close to the surface. The maximum rate at which radiation can be emitted from a surface at a temperature T is described by the Stefan-Boltzmann law, where sigma represents the Stefan-Boltzmann constant. A theoretical surface that emits radiation at this maximum rate is termed a blackbody, and the radiation it emits is called blackbody radiation. In reality, the radiation emitted by actual surfaces is always less than that emitted by a blackbody at the same temperature. The factor epsilon represents emissivity, a property of surfaces. If you enjoyed this video, don't forget to like, comment, and subscribe for more content like this. See you in the next one.